Hi, I'm Antonio Sala. In this video, we are continuing with our study of ellipsoids and their relation with positive definite matrices, and in particular we will discuss inclusion when one ellipsoid is inside another one, and we'll also discuss tangent sphere to an ellipsoid. Basically, an ellipsoid was the shape generated by this inequality, where P was a positive definite matrix. Anyway, we can also write them in inverted form, if so wished. Both ways are equivalent if ellipsoids are not degenerate, if both P and Q are non-singular. The interpretation is sort of that if I have an ellipsoid in non-inverted form, then P is inversely proportional to the square of size. The semi-axis length is 1 over square root of eigenvalues of P, and in the inverted form, Q is directly proportional to the square of size. So now we are going to discuss how to determine if one ellipsoid labeled as ellipsoid 1, described by this inequality, is inside some other ellipsoid, ellipsoid 2, described by this inequality. We'll discuss here the direct form, and inverse form will be discussed in the next slide. So, the main result is that P2 must be smaller than P1. This can be considered as a sort of informal inequality. Formally, it must be understood as this thing. Matrix P1 minus P2 must be a positive semi-definite one. Let us first justify it in intuitive terms. We just said that in this non-inverted representation, the bigger P is, the smaller the ellipsoid ends up being. So, if P1 must describe the small ellipsoid, then P1 must be bigger than P2. So this is kind of the intuition behind this inequality, which formally is the one at the right. Once we understand somehow the intuition, let us go with a formal proof. Then this is an if and only if condition, so we will prove implication in both ways as follows. Let us consider the if case, saying that this P1 minus P2 is a positive semi-definite matrix, means that for all x, this scalar inequality must hold. X transposed P1 minus P2, x must be non-negative. But if that happens for all x, then let us consider one x inside ellipsoid 1, so it will verify this inequality. But, well, this means that x transpose P1x is greater than or equal to x transpose P2x, so x transpose P2x is less than x transpose P1x, and if this was less than 1, then we have just written that x transposed P2x is less than 1, so indeed, if this positive definite condition holds, 1 is a subset of 2. So this proves implication in one direction. Let us now prove it in the other direction by proving that if this inequality does not hold, then 1 is not inside 2. So let us now imagine that this inequality does not hold for all x. Then there is some psi in which this thing is negative, which means that for that psi this happens. As this thing is homogeneous quadratic in psi, if I multiply psi by 10, then both sides will multiply by 10 squared, so I can expand or contract psi along the line, and this will still hold. So there is no loss of generality in assuming that that psi verifies this, that it's in the edge of 1. because if I had one in which this thing were 100, then I would divide it by 10 to have this. So we have a point at the edge of ellipsoid 1, but in that case, this psi is outside ellipsoid 2. So if this condition does not hold, then we have proven that this happens for some point in the edge of 1 that it's not in 2, so ellipsoids are not included. So if this matrix inequality holds, 1 is inside 2, and if it does not hold, 1 is not inside 2. So this is why we prove the if and only if condition for inclusion as our main result in non-inverted form. Let us now consider the case in inverted form. So I wish to know whether this ellipsoid is inside this one or not. In order for that to happen, the intuitive idea is that Q2 must be larger than Q1, formally understood as this matrix inequality. Q2 minus Q1 must be a positive semi-definite matrix. Again, first, let us discuss the intuition. When an ellipsoid is expressed in inverted form, the larger Q is, the larger the ellipsoid is. Q is directly proportional to the square size. So if ellipsoid 2 must be the bigger one, then Q2 must be the big matrix, so Q2 minus Q1 must be positive. So this is the intuition. The proof will make use of the discussion here and some lemma called sure complement, which we have down here. If we know for sure that A and C are two strictly positive definite matrix, all eigenvalues strictly larger than 0, then we can prove this chain of equivalences. This is a widely used in linear matrix inequality control, but we'll omit the proof here, but we'll use this thing. In some cases, we can transform a quadratic inequality in some matrices A, B, C, and C, quadratic in B, into a linear inequality in matrices A, B, C minus 1, and switching the order of rows and column, we can go back to this quadratic inequality in C minus 1, A minus 1, and B. So now, if these ellipsoids are not degenerate, I will call P1 as the inverse of Q1, I will call P2 as the inverse of Q2, and if they are not degenerate, P1 and P2 will be strictly positive definite. And then, from previous slide, 1 will be inside 2 if and only if this thing holds. So numerically, this would be enough and I would need no further proofs. I just invert Q's and check the inequality on the inverted matrices. But okay, using sure complement, we can theoretically prove that we don't need to carry out such inversion as follows. If I consider P1 to be A in this sure stuff at the bottom, I consider B and B transposed because they are equal to be identity matrices, and I consider C to be P2, then we can change to this 2 by 2 block matrix with P2 inverted by this sure formula, and then using the fact that B is identity, we can just write this thing with the sure formula, and the last expression is the one we were seeking, Q2 minus Q1. So we have proved that if and only if Q2 minus Q1 is positive semi-definite, so Q2 is larger than Q1 in informal terms, then ellipsoid 2 contains ellipsoid 1. So this ends the proof in inverted form. Let us have a look to the meaning in MATLAB. If we have two ellipses defined by P1 and P2, then, well, from the eigenvalues, we can say nothing about the inclusion. We would be able to say that only in the case of spheres, more on that later. But from here, we can say nothing. What we can say about inclusion is that we can say something about whether one is included in the other by analyzing the eigenvalues of the difference. In particular, P1 minus P2 is negative semidefinite, so it means that P2 minus P1 is positive semidefinite. So this inequality holds in reverse when switching sides of P1 and P2. What this means is that ellipsoid 2 is inside ellipsoid 1. If I draw with F implicit, indeed we see that ellipsoid 2 is inside ellipsoid 1, and as we have a zero eigenvalue, the ellipsoids are tangent, in the sense that if I make, let's say, ellipsoid 2 a little bit larger, which means making P2 smaller, for instance, I will make P2 10% larger, dividing by 1.1 squared, well, in that case, P1 minus P2 has one negative and one positive eigenvalue, so we can say nothing on whether P1 is inside P2 or P2 is inside P1. Neither of the two inclusions hold, as we see here. We cannot say anything about inclusion, and that is detected in matrices with one positive and one negative eigenvalue of the difference of p's. Of course, if I make P1 10% larger, then both eigenvalues here are negative, which means that 2 is strictly inside P1. Here we have it, no longer tangent. To finish the video, we will discuss a corollary when either ellipsoid 1 or ellipsoid 2 is a sphere. Because, well, sphere of radius rule is defined by this inequality. So, let us now consider having an ellipsoid and wishing to know whether this ellipsoid is inside a given sphere. Well, then we apply the previous result, saying that the ellipsoid given by matrix P is inside this outer sphere if its P matrix of the sphere, which is this one, is smaller than the P matrix of the ellipsoid, because the smaller the matrix in the middle here, the larger the ellipsoid. So the small thing must have the large P matrix. This is a direct application of what we just said, but it has a meaning in terms of eigenvalues. Because if I consider the minimum eigenvalue and eigenvector of P, then x transpose Px will be larger or equal than x transpose and the minimum eigenvalue times x, because the components of an arbitrary x in the other eigenvector directions will be amplified more than lambda minimum. So this implies that the minimum eigenvalue of P must be larger than the inverted square radius. So this is the conclusion on the outer sphere case in non-inverted form. And if we now consider the inverted form, the matrix inequality with the Q matrices, which in the case of a sphere is rho squared identity, because when I invert this I get this P, then we must reverse sign with the matrix inequalities as we saw in previous slide. So again, by considering now the case in which this thing will be lower than x transposed lambda max x, because we'll have equality when x is aligned with the eigenvector associated to the largest eigenvalue. In other cases it will be less than that. So this thing implies this thing, which in turn implies that the maximum eigenvalue of Q must be less than the square radius of the sphere. Last, if we consider whether a sphere is inside an ellipsoid, well, the only thing we must do is kind of changing the sign of these inequalities. So this ellipse will be larger than the given sphere if matrix P is smaller than row minus 2 identity, and with an analogous reasoning to the above. This means that all eigenvalues of P must be below row minus 2, and in inverted form, this thing is larger than the sphere of radius 2 if Q is larger than rho squared, which means that the minimum of the eigenvalues of Q must be larger than rho squared. So these are the conditions. Let us now see in MATLAB the meaning of this inclusion with spheres. If I have this P defining my ellipsoid, if I have the maximum and minimum eigenvalues, the thing is that, as we have it in direct form, the minimum eigenvalue of P will be inversely proportional to the square radius of a sphere outside it. So when this inequality becomes equality, we'll have a tangent sphere, and then on the other side, the maximum eigenvalue will be inversely proportional to the square of the radius of spheres inside it. So when we have an equality, we'll have a tangent sphere from the inside, which means that with these eigenvalues, which are proportional to the inverse square radius of something, well, then inverting and doing a square root, these 2 and 1 will be radius of the sphere outside, inverse of the minimum eigenvalue, or the sphere inside, inverse of the maximum eigenvalue. So if I plot with this code, you can analyze at will the ellipsoid and these spheres of radius 1, the green one, and radius 2, the purple one, then we see that they are the biggest sphere inside the ellipse, green one, and the smallest sphere outside the ellipse, purple one. So we finish with this. In this video we discussed inclusion of ellipsoids, which ended up depending on the positive semi-definiteness of the difference between the matrices that define the ellipsoids, and we explore the particular case of spheres, which gives minimum radius of the ellipsoid and maximum radius of the ellipsoid. So we end with this. Thanks for watching.